Okay, in this video I'd like to make a couple of points about work and conservation of energy and how you'll use them. And then I'll do one example problem that has multiple parts. And then more example problems can follow up in another video. So, all right, in this slide we have a force applied, which is 120 newtons, pushed to the right. That little squiggly lines in that arrow are just there to indicate that it is not to scale with the 5 newtons of frictional force pointed the other way. And then of course the distance of 0.800 meters does not need to be to scale to the forces at all because it's measuring a completely different quantity. We have our mass given, and we have the force of gravity pointed down and the normal force pointed up. The force of gravity, because this is OpenStax, is labeled W, like weight. And this is exactly the chapter, which is the reason why I wouldn't do that, because W means work, which is a scalar quantity, and they're using it here as weight, which is a vector, a type of force. So we've got a couple questions on here, though. This package is assumed to start at rest, and it's pushed horizontally through some distance d from where it currently is off to the right. And then it's asking what forces are causing acceleration of this box, what forces are causing a change of kinetic energy, and what forces are doing work. If you think you know the answer to these, go ahead and jot that down. All right, my answers are that I'm seeing all the forces that are acting here, but only the force applied and the frictional force are causing an acceleration of this box. The force applied is definitely causing an acceleration because it's pushing the box in the direction that it is moving, so you clearly will see it go faster and faster because of the force applied. If you weren't thinking that the force of friction causes an acceleration on the box, then I'm going to hazard a guess that it's because you forgot that a negative acceleration is an acceleration. But F equals ma, and so the frictional force, being a force, will cause an acceleration. The force of gravity and the normal force do not belong on here causing an acceleration because the box does not accelerate in that direction. It has a net force of 0 in the y direction. I want to point out, though, that if the box is accelerating, that means its velocity is changing. And both the force applied and the frictional force are contributing to that. They are each affecting how much the velocity changes, and that means they are each causing a change in the kinetic energy of the box, while the gravitational and normal forces are not. So that means which forces are doing work? Well, the force applied is doing positive work, the frictional force is doing negative work, and as we saw in the previous video, the gravitational force and normal force in this case are perpendicular to the displacement. Any force that is perpendicular to the displacement is doing no work. Therefore, it's causing no change in kinetic energy, and another way to say that is that it is not influencing the box's acceleration. Some follow-up questions would be how much work, for example, is done by just the applied force? And how much work is done just by the frictional force? And then what is the net work done on the box? Net work means total work, which is also the work done by the net force. So what you could do, let's answer A and B and then come back to C. And then D is what is the increase in kinetic energy over the distance of 0.800 meters to the right? And then in part E, how fast is the box going after it's gone that distance? I want to note for D and E in particular, you could find the net force, plug that into Newton's second law and determine the acceleration, and then put that into the time-independent kinematics equation and determine the final velocity that way. You could, and that's not a problem at all. That's not how I'm going to do it here. The work done by the applied force is the force times the displacement times the cosine theta, where theta is the angle between the applied force and the displacement. But the applied force and displacement are both to the right here, so there's cosine of theta where theta is 0 degrees. So cosine of 0 degrees is 1, and this turns into just 120 newtons times 0.800 meters, and that's 96 joules. How much work is done by friction is going to be found with the exact same equation, but now the force is 5 newtons and the distance is 0.800 meters, and the theta is 180 degrees, so I'm going to get a negative 4 joules. That's because the frictional force is pointing in a direction exactly opposite of the direction of displacement. The net work done on the box, there's two ways I could do this. One is to determine what the net force is, and then determine what the work is that's done by the net force. So I could take the net force of 115 newtons to the right and put that into the equation, 115 times the displacement times cosine theta. But the other thing I could do is I could just say 96 joules of work was done by the one force and negative 4 joules of work was done by the other, and I can add those as a scalar. I don't have to worry about any vectors or anything. Just say 96 plus minus 4. 92 joules of work total was done on the box. 92 joules of work was done on the box means the kinetic energy of the box increased by 92 joules. So how fast is the box going after this distance? Well, I don't know, but it started out with no velocity, and then you added 92 joules of energy to it, and the 92 joules is not spring potential energy or gravitational potential energy, it's kinetic. So I could take that 92 joules and put it into the kinetic energy equation and say that's equal to 1/2 mv squared. And if you do that and solve for v, and be sure that you don't just get v squared, but actually square root at the end, and be careful, I get 2.5 meters per second. It is going to the right, but it didn't ask me for a velocity here, so if it had been going to the left, it would have been fine to leave it as 2.5. Always a good idea, though, when your answer is something like a displacement or a speed or something like that, to double check where you asked for a vector answer, and if so, are you giving a vector answer? So this idea that the net work done on the box is the change in kinetic energy on the box, the textbook refers to this as the work energy theorem, and I don't usually emphasize that too much because work can also, or rather instead, increase the potential energy of an object, and it's sometimes a little confusing to know which one it is. So for example, in a problem like this one, this is an example that's actually not a problem, I guess, but it's given as an example in the textbook to emphasize that if you lift a heavy object, I think that's supposed to be a television, old-fashioned television, kind of looks like an accordion. I don't know what it is. Whatever this thing is, if you lift it straight up like person A is, using this rope and pulley, then when you've lifted it height h, you have increased the potential energy of your accordion television combination item. The person carrying it up the stairs also lifts the television accordion item to a height h. They have each given it the same change in gravitational potential energy. They have each done the same amount of work. So what I'm emphasizing here is you have these two people doing work on this item and not increasing its kinetic energy, but increasing instead its gravitational potential energy. So when you read about the work kinetic energy theorem, keep in mind that that is for a specific type of problem, and other problems involve instead potential energy. In that little experiment, I drop a ball and it starts out with gravitational potential energy, and then obviously as it's falling, that's turning into kinetic energy. It hits the ground and bounces back up, but not as high, and then continues to bounce, repeatedly bouncing to not as high as it previously had been. So this is just here to emphasize that energy is being lost from the ball, and in a system where energy is being lost from the ball, I'd like to know where that energy is going. It is conserved, it's got to be going somewhere. Where is it going? And where it's going is partly that it's making sound, like it requires some energy to create the sound that we heard. Partly it's actually heating the ball. I've seen people who do an experiment where they take a like a field hockey ball and they pierce it with a little digital thermometer, and they just sit there and bang it on the table for a long time, and you can see the temperature of it actually goes up several degrees. It was I thought it was an interesting experiment, but not interesting enough for me to replicate. This graph showing the kinetic and potential energies over a period of time for a lab a lot like that simple ball drop I just did shows that the mechanical energy drops over periods of time. This is as the ball bounces over and over again. So where is that total mechanical energy going? And we want to emphasize, when you can't find where it's going, it may very well be because it's being dissipated to the atmosphere, or the internal thermal energy of the object itself. We're not going to be calculating that sort of thing, but I want to emphasize that that energy is still out there. And so in more technical, advanced scientific and engineering situations, if you had to track that energy down, it would be something you could find if you were meticulous and went through and said what created that sound, why is the temperature increasing, etc. We're going to be doing problems that are a little bit more straightforward, though, things like this. How much work is done on the car? Well, they've only given me that a pushing force was applied to it, and I can tell that there's a gravitational force and a normal force, but if the only force that they're showing me is this person pushing the car to the left, then I would say that the work done on the car is equal to the force times the delta x times cosine theta. I like this slide because if you look at the top right here, it's got that delta E equals W equals F, and then the parallel lines, and then D equals Ft cosine theta. What they're trying to say here, if you ever see that in a resource, that's trying to say the amount of the force vector that is parallel to the displacement vector. Another way to say it is Fd cosine theta. So if you ever see that somewhere, that's saying the same thing as what we're saying with our equation sheet. How much work is done on the car is going to be the applied force, the 350 newtons in this case, times the displacement of 25 meters. And it does not matter whether this person is pushing to the right or to the left. This is because it's a scalar, and because even if you put the negatives in, you would have the negative distance times the negative displacement times the negative force. But I don't want you to put them in, and that's why on the equation sheet I did put them in as absolute values. The cosine theta will take care of it. He's pushing it in the same direction that it's displacing, so the work is positive, which is good if you're trying to push a car because you want it to go faster after you've pushed it. So this is just like the earlier problem. He applies that force for that distance. He's added 8750 joules to the system, and it's showing up as kinetic energy. It's manifesting as a final kinetic energy. So you can solve for the final velocity or final speed of the car like that. And he's got it up to 3.9 meters per second, which is, that's not too bad. Good for him. The next couple slides do not have questions or numbers to them, but they're just here to emphasize that if you are given a situation where there's no friction, no outside applied force, and you just have conservation of energy, this is very qualitative to show this bar graph situation here. But notice the bar graph at point A, the bar graphs combined at point B, and the bar graph at point C, they would all add up to the same total energy. And that's how you would actually solve a problem, is you would be given everything except the one variable you're being asked for. So whether you are being asked for the original height or the final speed or whatever it is, and that's the example we're going to get into in just a moment. This would apply for a situation like this skier, and it would apply for a situation like this roller coaster. Notice in each of these situations, these are not all flat surfaces. So you might be able to determine the acceleration at point A, or you might be able to determine the acceleration on the incline between point B and C, but on the curves there, that's actually pretty tough to try to do. And a curved path, including like a pendulum, is a really good sign that you would rather do this as an energy problem. This problem, 550 kilogram roller coaster car has a velocity of 0.25 meters per second at point B. That's 30 meters above the lowest point on the frictionless track, and it's asking us how fast is the roller coaster going at each of the other points. I left off point A on here because that's the place where you would be doing your initial work to get the car up there. And of course at the highest point, I don't know if you've ever been on a roller coaster. I'm just going to assume that you have not, and I'm going to tell you, it goes slowest at point B at the highest hill, and then it goes really fast at point C. It goes faster still at point D, and then as it comes up the hill at point E and point F, it slows down a little bit from point D. D is where it's fastest. So now you understand how a roller coaster works. You may not even want to go on one due to that riveting explanation I just gave. Let me go through the math and explain how fast it's actually going at each of those other points. The way I would solve this is I would say the energy at one of the points that I know a lot of information about equals the energy at each of the other points. It's frictionless track, so this is true. E at B equals the mechanical energy E at C and at D and at E and at F. B is the one that I know the most information about, so that's the one I definitely want to include, and C is the one I want to include here because I'm going to find out how fast the roller coaster is going at point C. At point B, there's a kinetic energy and a gravitational potential energy. At point C, there's a kinetic energy and gravitational potential energy. The kinetic energy at point B is 1/2 mv squared, and the gravitational potential energy is mg delta y, where delta y is the height above the lowest point. They gave that to us, that's 30 meters, and they gave us the speed at point B, that was the 0.25 meters per second. They even gave us the mass, so all of the B side of this equation is ready to go. On the C side, the 1/2 mv squared is how I will find the speed at point C. I know the mass, but I don't know the speed. And then, of course, the gravitational potential energy at point C is mg delta y, and delta y is the height above the lowest point. And they told me at point C, that's 20 meters. An astute observer might have noticed that mass appears in each of these, so I can divide it out. If you were not that astute in that moment, that's actually fine. You just are multiplying in 550 kilograms to several of the terms and then dividing it out later, and you get the exact same answer. That's all. So it's okay if that happens. But I'm going to divide out the masses here, not because I'm astute, but because I've been doing this for 20-something years, so I knew that was just a little trick that I remembered. That's all. Hopefully you'll remember it. It does speed things up slightly when you're doing your math. I know everything on this line except what I'm trying to solve for, which is the speed at C, the velocity at C. So I start plugging in my numbers. Please be very careful to make sure that your speed at point B goes in for the V subscript B. Your delta y at point B goes in for the delta y at point B. I know that's an obvious thing to say, but this is the part where I see students making the most mistakes, is the simple substitution, because there's a lot of variables to keep track of, and it's very easy to put the wrong variable in the wrong spot. In fact, you should be checking my math to see whether I did that, because that's an easy mistake to make. I found that at point C, the roller coaster is up to 14 meters per second, which is pretty fast. So that's how I found how fast it's going at point C. They gave us point B. How am I going to find out how fast it's going at point D and E and F? It's the exact same process. So at point D, you would do the exact same thing using the information you know about points B or C. I'm going to go a little bit faster through the slides here and encourage you to actually pause it, calculate it, and check it against your own. But at point D, you know that you're 0 meters above the ground because that's what they gave us. And so that turns into just a 0 for the gravitational potential energy. And I therefore got that at point D, it's going even faster than at point C, 24.25 meters per second, which is really fast. That's a very exciting roller coaster. All right, at point E, it's the exact same thing. And all that's different is that now you're at 10 meters height. So you should be going faster than at point C, but slower than at point D. Sure enough, I calculate that you are going 19.8 meters per second at point E, and then point F is farther up the hill, so you should be going even slower. And so if I go through, I find the exact same process, 17.1 meters per second, meaning that given the heights, I was able to find the speeds at all the other places, but they did have to give me how fast I was going at point B to get me started here. The mass didn't matter because it was just gravitational potential energy and kinetic energy. The mass would matter if I had the spring constant, the spring energy involved in this equation somehow, or if we had friction involved and we had to calculate the work done by friction. If it's just kinetic and potential energy, though, the mass divides out and the math is really just going to be a matter of you're asked for one variable and you're given all of the other variables. All right, that was the only example I really wanted to walk through rigorously in this video, and I will do some more examples in a follow-up video.